September 7th, 1940. 8:47 p.m., Bethnal Green, East London. The air raid siren's wail cuts through the evening like a blade dragged across steel. Margaret Whitman doesn't flinch anymore. She's heard it 17 times in the past month. She's kneeling in her garden, dirt under her fingernails, trying to salvage what's left of her tomatoes before the bombs come. Above her, the sky rumbles. Not thunder, engines. Hundreds of them, growing louder, a mechanical swarm that makes the ground vibrate beneath her knees. She looks up and her breath catches. The evening sun hasn't fully set, and she can see them clearly. Black crosses on wings, stretched across the horizon like a plague of locusts. Heinkel 111s, Dornier 17s, more than she can count, flying in tight formation, their bellies fat with incendiaries and high explosives. The Luftwaffe is here to burn London to ash. She runs for the Anderson shelter in her backyard, the corrugated metal half buried in the earth, and throws herself inside just as the first bombs hit 3 streets over. The concussion wave slams the shelter door behind her. The sound is beyond hearing. It's a physical force that crushes her chest, makes her teeth ache, turns her organs to jelly. Through the ventilation slits, she sees the sky turn orange, then white, then orange again. The air smells like burning rubber, and something sweet and horrible she refuses to identify. This is the 3rd night this week. The Luftwaffe comes after dark because darkness makes them invisible. British anti-aircraft guns fire blindly into the void, hoping to hit something, anything. Searchlights sweep the sky in desperate arcs, but the bombers stay high, hidden in the clouds, unreachable, untouchable. The gunners on the ground are shooting at sounds and shadows. Sometimes they get lucky, most times they don't. 4 miles away, in a sandbagged emplacement near the Thames, Gunner Thomas Aldridge stares up at the sky through the sights of his 3.7-inch anti-aircraft gun. He can hear them perfectly, the distinctive asynchronous drone of German engines, the whistle of falling bombs, the crump-crump-crump of explosions marching across the city. But he can't see them, not a single silhouette. The searchlight crews are doing their best, stabbing beams of light into the darkness, but the bombers are too high, too dispersed, and the beams can't find them fast enough. His gun crew has fired 63 rounds tonight. They think they might have hit something 2 nights ago. Maybe, because they heard an engine coughing somewhere in the dark and found wreckage in the morning. Maybe. Aldridge cranks the elevation wheel, following the sound, waiting for the officer to give the command. The spotter is shouting bearings, guessing angles, estimating altitude based on nothing but sound and prayer. They fire. The gun bucks, the shell screams into the night, and somewhere up there it explodes into a harmless white puff that no one sees. Aldridge doesn't know if he's even close. No one does. This is what losing feels like. By morning, 436 Londoners are dead. 2,000 buildings are damaged or destroyed. The fires burn for 3 days, and the Luftwaffe will be back tomorrow night, and the night after that, and the night after that, because they own the darkness. The British have anti-aircraft guns. They have searchlights. They have brave crews willing to die to defend their city. But they're blind. They're firing at ghosts. The RAF sends up night fighters, Bristol bow fighters and obsolete Blenheims, but finding a single bomber in the vast black ocean of the night sky is like finding a needle in a haystack the size of England. The pilots fly patrol patterns, straining their eyes until tears stream down their faces, praying to stumble across an enemy silhouette against the stars. Some nights they find one. Most nights they find nothing. The Germans know this. They know the British can't see them. And they're using that knowledge to methodically dismantle British cities, one neighborhood at a time, knowing there's almost nothing the British can do to stop them. In the cabinet war rooms deep beneath Whitehall, Winston Churchill receives the casualty reports with a face carved from stone. He knows the numbers. At this rate, German bombers will kill tens of thousands of civilians before the year is out. British morale is holding, barely, but morale doesn't stop high explosives. What stops bombers is shooting them down before they reach their targets, and you can't shoot what you can't see. Britain's survival depends on solving an impossible problem. How do you find a tiny aircraft in an infinite sky in complete darkness? How do you see in the dark? The answer exists, but it's incomplete, inadequate, not good enough. It's called radar, radio detection and ranging, and the British have it, sort of. The chain home stations ringing Britain's coast can detect incoming raids from 70 miles away, giving precious minutes of warning, but those radar sets are massive installations with towers over 300 feet tall, and they can only point in one direction. Out to sea, scanning for distant threats. They can't track individual aircraft with precision. They can't be mounted in a fighter plane. They can't guide a pilot's eyes to a target in the pitch-black sky. The radar Britain has isn't enough to win this war. It's enough to know death is coming. It's not enough to stop it. 300 miles north, in a nondescript university laboratory in Birmingham, two men are trying to do something every physicist in the world believes is impossible. Their names are John Randall and Harry Boot, and they're standing in front of a workbench covered in copper cylinders, vacuum tubes, and enough electrical equipment to power a small factory. The object they're building is roughly the size of a dinner plate, a solid copper disc with 8 cavities drilled into it like the chambers of a revolver, and it looks like absolutely nothing special. It looks like a piece of industrial scrap, but if it works, if they can make it work, it will change everything. The problem is wavelength. Radio waves used by existing radar systems are too long, measured in meters, and long wavelengths mean fuzzy, imprecise detection. You can tell something big is out there, roughly where it is, but you can't tell exactly how far, exactly what bearing, and you certainly can't tell if it's one bomber or 50 flying in formation. What Britain needs is microwave radar, radio waves measured in centimeters, not meters, because short wavelengths mean precision, detail, clarity. Microwave radar could pinpoint a single aircraft's position to within yards. It could fit inside a fighter plane's nose. It could give British gunners exact coordinates instead of educated guesses. But generating powerful microwaves requires technology that doesn't exist yet. The magnetron, a device that generates radio waves using electrons spiraling in a magnetic field, has been around since the 1920s. But every version anyone's built produces either long wavelengths or pathetically weak signals. You need both short wavelengths and enormous power simultaneously in a package small enough to be useful. Every major research institution in Britain, Germany, and America has concluded it can't be done, not with current technology, maybe not ever. The physics doesn't work. The engineering is impossible. Randall and Boot don't care what's impossible. They have 8 months to make it work anyway, because Churchill's scientific advisor, a physicist named Henry Tizard, has told them in no uncertain terms that Britain will lose this war without better radar. No pressure. Just save civilization before Christmas. Boot is adjusting the magnetic field strength, watching the oscilloscope, while Randall checks the vacuum seal for the 100th time. The theory is sound, they think maybe. Electrons injected into the center should spiral outward through the cavities, and if the cavities are the right size, the electrons should resonate at microwave frequencies, amplifying the signal with each pass, building power exponentially. In theory, they've been trying for weeks. Every test has produced either nothing or a brief flicker before the whole apparatus melts from the heat. Boot makes a final adjustment to the cathode voltage. Randall nods. They throw the switch. The magnetron hums. The oscilloscope spikes. The needle on the power meter slams so hard to the right that for a moment they think the meter is broken. But it's not broken. The magnetron is generating microwaves at 10 centimeters wavelength. And it's producing not milliwatts, not watts, but kilowatts. 400 watts of continuous microwave power, more than any device this size has ever produced. More than anyone thought possible from a magnetron. More than some entire radar installations currently achieve. Boot and Randall stare at the instruments in silence. Then they stare at each other. Then they run the test again to make sure they're not hallucinating. Same result. The impossible device is working. The cavity magnetron, a solid copper disc with holes in it, is generating enough microwave power to revolutionize radar, and it's doing it in a package the size of a large grapefruit. This is the weapon that will save Britain, though it doesn't look like a weapon. It looks like a piece of plumbing. But weapons aren't always guns and bombs. Sometimes a weapon is a way to see your enemy in the dark. The breakthrough spreads through Britain's scientific establishment like electricity through a wire. Within weeks, engineers at the Telecommunications Research Establishment in Dorset are building prototype radar sets around the magnetron, miniaturized units that can generate a beam of microwave energy, bounce it off a target, and measured the return signal with astonishing precision. The first successful test happens on a cold morning in March 1941, when a prototype mounted on a hilltop detects a training aircraft at 40 miles distance and tracks it continuously, painting a bright, sharp echo on the cathode ray tube display. The operators can see the aircraft's altitude, bearing, speed, and range updated every second. They can watch it turn. They can see individual aircraft in a formation. This is what precision looks like. But Randall and Boot aren't the only names in this story. And this is where the narrative becomes complicated. Where national pride and scientific collaboration tangle together in ways that historians will argue about for decades. The cavity magnetron wasn't invented from nothing. It built on years of research into magnetron design, work done by scientists across Europe and America, incremental advances that made the Birmingham breakthrough possible. And among those scientists was a Norwegian. His name was Odd Dahl, and his contribution to radar technology came not from Birmingham, but from a different war entirely, the one being fought in occupied Norway, in the shadows, in the frozen forests where resistance fighters hid from German patrols, and scientists smuggled research across borders at the risk of their lives. Dahl was a nuclear physicist before the war, working in Oslo, studying cosmic rays and atomic structure, the kind of abstract research that seems useless until suddenly it isn't. When Germany invaded Norway in April 1940, Dahl made a choice. He could stay, keep his head down, maybe survive. Or he could run, taking with him everything he knew about high-frequency electronics and microwave physics, knowledge the Germans would very much like to have, and the British desperately needed. He chose to run. He made his way across the mountains to Sweden, then to Britain, carrying nothing but the clothes on his back and a head full of physics that would help British scientists understand how to make the magnetron stable, how to prevent it from destroying itself, how to manufacture it reliably under wartime conditions. Dahl's expertise in high-frequency resonance and vacuum tube design filled crucial gaps in British knowledge. He worked alongside Randall, Boot, and dozens of other scientists at the TRE, solving problems no one had encountered before because no one had ever built anything like this. The magnetron is ready. Now it needs to become a weapon. By the summer of 1941, British engineers have transformed the laboratory curiosity into production models, manufacturing cavity magnetrons by the dozens, then hundreds, each one identical to the last. Each one capable of generating the microwave pulses that will paint German bombers on a radar screen with crystalline clarity. The magnetrons are being installed in a new generation of radar systems designated AI Mark 7th, Airborne Interception, 7th iteration. And these sets are nothing like the primitive equipment British night fighters have been limping along with for the past year. The Mark 7 is compact enough to fit in a fighter's nose, powerful enough to detect a bomber from 4 miles away, and precise enough to guide a pilot directly onto an enemy's tail in complete darkness. It's everything Britain needs. The question is whether it works outside a laboratory, in the real chaos of combat, when people are trying to kill you. Flight Lieutenant Robert Brahm doesn't trust technology. He's 20 years old, already an ace with 9 confirmed kills, and he's survived this long by trusting his eyes, his instincts, and the Hispano cannons mounted in his Beaufighter's wings. Now the ground crew is bolting a strange apparatus into his aircraft's nose, a radar set with a display screen mounted in the cockpit, a glowing green cathode ray tube that's supposed to show him where German bombers are hiding in the dark.
His radar operator, Sergeant William Styx Gregory, will sit behind him watching the screen, calling out bearings and ranges, guiding him toward targets he can't see.
Graham is skeptical. He's flown 23 night combat sorties with the old radar, and it's been worse than useless, fuzzy, unreliable, showing phantom echoes that disappear when you chase them, failing at critical moments, adding workload without adding kills. But his commanding officer assures him this new set is different, revolutionary, built around some kind of miracle device the boffins cooked up that makes the impossible possible. Graham will believe it when he sees it, or rather, when he shoots something because of it. September 19, 1941, 11:23 p.m., 6,000 feet over Kent. Brahm's Beaufighter climbs into the darkness. Engines roaring, navigation lights extinguished, hunting. Ground control has vectored him toward an incoming raid, Multiple bogies inbound from France, heading for London. Altitude estimated at 15,000 feet. Bram can't see anything. The night is overcast. No moon, no stars, nothing but black infinity in every direction. He's flying on instruments, trusting his altimeter and compass, waiting for Gregory to find something on the magic screen. Behind him, Gregory is hunched over the radar display, watching the green glow, adjusting the gain, tuning the frequency. And then he sees it. A bright pip on the screen, sharp and clear, range 3 miles, slightly above them, bearing 030 degrees. Contact, Gregory says into the intercom, his voice steady. 3 miles, Angels 15, bearing 030. Bram banks right, pushes the throttles forward, begins climbing. Gregory keeps calling ranges. 2.5 miles. 2 miles. Bearing steady. He's not evading, he doesn't know we're here. This has never happened before. Every previous intercept has been fumbling in the dark, chasing ghosts, arriving at empty sky. But the pip on Gregory's screen isn't moving randomly. It's holding course and altitude, solid, real, trackable. Bram keeps his eyes forward, searching the darkness, trusting his radar operator completely now because there's no other choice. 1 mile. Bearing 025. Same altitude. Bram strains his eyes. Nothing. Just darkness. Half mile. Dead ahead. And then Bram sees it. A dark shape against slightly less dark sky. A twin-engine silhouette. Exhaust flames glowing faintly from the engines. Heinkel 111. The bomber crew has no idea a British fighter is sitting 200 yards behind them, cannons armed, finger on the trigger. Bram has done this 9 times before, but never this easily, never this perfectly guided to a target like a missile on rails. He closes to 150 yards, centers the pipper on the Heinkel's fuselage, and squeezes the trigger. 4 20mm Hispano cannons erupt simultaneously, pouring explosive shells into the bomber's port wing and fuselage. The Heinkel's wing root explodes in orange flame, fuel igniting, pieces of aluminum spinning away into the darkness. The bomber rolls left, completely out of control, and begins the long fall to Earth. Bram doesn't follow it down. He's already looking for the next target. "Give me another one, Sticks," he says. Gregory is grinning at his radar screen. "I've got 2 more. Bearing 110, 3 miles. By dawn, Braham has shot down 3 German bombers in a single night. All perfect intercepts, all guided by the radar set that actually works. That turns night fighting from desperate guesswork into a cold equation of vectors and closure rates. The ground crew finds him after he lands, demanding to know what happened, because 3 kills in one sortie is almost unheard of for a night fighter. Bram just points at the radar set. "That," he says. "That's what happened. Whatever the boffins did, it works." The word spreads through RAF Fighter Command like wildfire. The new radar works. The Mark 7 actually works. Pilots who've been flying blind for a year suddenly have night vision, electronic eyes that pierce the darkness better than their own. Production of the AI Mark 7 accelerates. More Beaufighters get the new radar, then Mosquitoes, then the new Beaufighter Mark 6 variant, designed specifically around the magnetron-based system. And the German bomber crews start dying in numbers they've never experienced before. October 1941. November. December. The Luftwaffe's night bombing campaign, once nearly unstoppable, begins to hemorrhage aircraft. Bombers that used to reach London unmolested now disappear over the channel, shot down by fighters they never saw coming, guided by radar they don't know exists. German crews report being attacked out of nowhere by fighters that find them in clouds, in darkness, in weather conditions that should make interception impossible. Luftwaffe intelligence analysts pore over after-action reports, trying to understand how the British night fighter force suddenly became lethally effective. Some crews claim the British have cat-eyed pilots, mutants who can see in the dark. Others insist the RAF is using infrared detection, tracking engine heat. The truth, that Britain has leapfrogged German radar technology by 5 years through a single inspired invention, doesn't occur to them because it shouldn't be possible. Germany has excellent radar scientists, generously funded research programs, and access to Europe's finest technical universities. If microwave radar were feasible, German scientists would have built it first. The idea that Britain, besieged and desperate, somehow invented something Germany's superior research establishment hasn't achieved is absurd. So German intelligence doesn't look for microwave radar. They look for everything else. The cavity magnetron is Britain's most closely guarded secret. More sensitive than Ultra, more valuable than the location of Churchill's bunkers. Because if Germany discovers what Britain has and manages to replicate it, the entire strategic balance shifts overnight. Every RAF aircraft carrying the Mark 7 radar has explicit orders. If you're going down over enemy territory, destroy the radar set. Smash it with an axe. Burn it with thermite grenades. Put a bullet through the magnetron. Do whatever it takes to ensure the Germans don't get their hands on an intact unit. Pilots are briefed in rooms with armed guards at the doors. They're told the radar they're carrying represents years of research, thousands of man-hours, scientific breakthroughs the enemy would kill to possess. They're told that if they're shot down and survive, their first duty, before evading, before escaping, before anything else, is to utterly annihilate the radar equipment. Some pilots joke darkly that the magnetron has a higher priority than they do. They're not entirely wrong. But technology doesn't stay secret forever. Not in war. Not when hundreds of aircraft are flying with it every night. When production lines are churning out thousands of magnetrons. When dozens of ground radar stations around Britain are using magnetron-based systems to track aircraft with unprecedented precision. It's not a question of whether Germany will eventually capture one. It's a question of when and how much damage that discovery will cause. The nightmare scenario keeps British intelligence officers awake at night. A Beaufighter or Mosquito shot down over occupied Europe, crash landing intact enough that the radar set survives. German troops securing the wreckage before the crew can destroy it. Scientists in Berlin examining the magnetron and realizing what they're looking at. If that happens, Germany's scientists will reverse engineer it within months. German night fighters will get microwave radar. German anti-aircraft batteries will track RAF bombers with perfect accuracy. The technology that's winning Britain the night war will become the technology that loses it. February 2nd, 1943. 1:47 a.m., 12,000 feet over Rotterdam. Squadron leader Edward Crewe is flying a Mosquito night fighter on an intruder mission, hunting for German aircraft over occupied Holland, when his starboard engine takes a 20mm shell from a German night fighter he never saw coming. The Merlin engine disintegrates in a spray of oil and metal fragments, the propeller windmilling uselessly, and suddenly Crewe's sleek fighter is a brick with one working wing. His radar operator, Flight Lieutenant Harold Faulkner, is already reaching for the destruction protocol, a thermite grenade mounted next to the radar set, designed to melt the magnetron into slag. But Crewe is fighting the controls, trying to keep the Mosquito airborne long enough to make it across the North Sea to England. And every second they stay in the air is another second the equipment stays intact. The aircraft is losing altitude at 300 feet per minute. They're not going to make it. Crewe knows it. Faulkner knows it. We're going down, Crewe says, his voice flat, stating a fact. Do it now. Faulkner pulls the grenade pin. The thermite ignites with a magnesium-white flare, burning at 4,000 degrees, and the radar set melts like wax. The magnetron's copper cavities collapsing, the vacuum tube shattering. Everything that makes the system work transforming into a puddle of molten metal and glass. Smoke fills the cockpit. Crewe puts the Mosquito down in a field outside Rotterdam, a wheels-up landing that tears the fuselage open like a sardine can, but doesn't kill them. They're both conscious, both injured but mobile. German troops are already converging on the crash site. They've seen the burning wreckage. They're coming fast. Crewe and Faulkner crawl out of the wreck, stagger away into the darkness, begin evading, trying to reach the Dutch resistance network that can smuggle them back to England. Behind them, German soldiers secure the crashed Mosquito. They find the radar set, or what's left of it, a melted, unrecognizable mass of metal still glowing red-hot. Whatever it was, it's destroyed beyond any hope of analysis. The British crew did their job. The secret is safe for now, but statistics are inevitable. Hundreds of aircraft, thousands of sorties, and eventually the law of averages catches up. May 13th, 1943. A Beaufighter from 255 Squadron takes flak over northern France, the pilot killed instantly. The aircraft going down nose first, but at an angle shallow enough that the fuselage doesn't fully disintegrate on impact. The radar operator is unconscious, bleeding from a head wound, unable to activate the destruction protocol. German troops reach the wreck within minutes. They find the radar set intact, still mounted in the nose, the magnetron visible behind its protective housing. This is the nightmare scenario. Wehrmacht signals intelligence, photographs everything, crates the entire radar assembly, and ships it by priority transport to Berlin. Within 48 hours, the cavity magnetron is sitting on a laboratory bench in front of Germany's best radar scientists, who examine it with a mixture of awe and horror. The device is impossibly small. The power output is impossibly high. The engineering is impossibly elegant. And it's British. Germany's scientists, who've been working on magnetron designs for years with minimal success, are looking at a technology that's at least 5 years ahead of their own research. Maybe 10. Dr. Wilhelm Runge, one of Germany's leading experts on microwave generation, writes in his initial assessment report, "The British magnetron represents a fundamental breakthrough in cavity resonator design. If this technology is operational in RAF night fighters, and if production is widespread, then our current understanding of British radar capabilities is catastrophically incomplete. We have underestimated both British scientific capacity and the sophistication of their defensive systems." The report makes its way up the chain of command, each level adding its own notes of alarm. How long have the British had this? How many aircraft carry it? Why didn't German intelligence detect it earlier? And most importantly, can Germany replicate it? The answer to the last question is yes, technically, but not quickly. The magnetron's design is deceptively simple, but manufacturing it requires precision machining, exotic materials, and industrial capacity that Germany's war economy is already struggling to provide. German factories are producing tanks, aircraft, and ammunition as fast as possible. Retooling production lines to manufacture magnetrons will take months, maybe a year, and the materials, high-purity copper, specialized vacuum tubes, precision magnets, are in short supply. By the time Germany has operational magnetron-based radar, the war's strategic situation may have changed completely. But the discovery comes too late to save the Luftwaffe's bomber force, because by mid-1943, the damage is already catastrophic and irreversible. The numbers tell a story of systematic destruction. In 1940, during the height of the Blitz, German bombers operated over Britain with roughly 2% loss rates per sortie. Acceptable, sustainable, the kind of attrition any air force can absorb while maintaining offensive operations. By late 1941, after the widespread deployment of magnetron-based radar, that loss rate climbs to 5%. By early 1942, it's 8%. By the summer of 1942, it's pushing 12%, and at that rate, bomber crews have less than a 10% chance of surviving a full tour of 30 missions. The Luftwaffe's night bombing campaign doesn't end with a dramatic final battle. It ends with a slow mathematical bleed, with bomber groups hemorrhaging aircraft and experienced crews faster than training schools can replace them. Until one day the High Command looks at the numbers and realizes they're throwing away men and machines for negligible strategic effect. The night offensive against Britain quietly stops. German bombers are redeployed to the Eastern Front, where Russian night fighters don't have microwave radar, where the old tactics still work. RAF Fighter Command's kill count tells the same story from the opposite side. In 1940, British night fighters shoot down approximately 40 German bombers total for the entire year. In 1941, after the Mark 7 enters service, that number jumps to 421. In 1942, it's over 800. British night fighter aces are being made overnight. Pilots like Braham, like John Cunningham, like Bransey Burbridge, who will end the war with 21 confirmed night kills. All but 2 of them achieved with magnetron radar, guiding him onto targets he never could have found with his eyes alone. These men become legends, celebrated in newspapers, their photographs on recruiting posters, but they know the truth. They're not superhuman. They're not blessed with cat-like vision. They're ordinary pilots with an extraordinary weapon, an electronic eye that turns night into day, that makes the invisible visible. The real heroes, they'll say later, are the scientists who built the tool that let them do their jobs. Back in the laboratories, those scientists are already pushing the technology further. The cavity magnetron is just the beginning. Engineers develop improved versions. More power, better reliability, smaller size, different frequencies for different applications. Magnetrons go into naval radar sets, letting British destroyers detect surfaced U-boats at 10 miles in complete darkness. They go into airborne surface search radar, allowing Coastal Command aircraft to find submarines on the surface at night, when the U-boats used to be safe. They go into H-2S ground mapping radar, giving RAF bomber crews the ability to navigate and identify targets through clouds and darkness, turning the strategic bombing campaign from a blunt instrument into a precision tool. The magnetron appears in fire control radar for anti-aircraft guns, replacing human guesswork with electronic calculation, making every shell count. By 1944, magnetron-based radar is so ubiquitous in British and American military equipment that young soldiers assume it's always existed, that everyone has it, that it's just standard technology like radio or the combustion engine. They don't know they're using a miracle. They don't know that 3 years earlier this technology was considered impossible. They don't know about Randall and Booth's 8-month sprint to build something that shouldn't work. They don't know about Odd Dahl and the other scientists who fled occupied countries, carrying their knowledge to Britain, contributing pieces of the puzzle that made the breakthrough possible. They don't know about the pilots who died destroying radar sets to keep the secret safe, who burned their aircraft rather than let the enemy learn what was inside. All these soldiers know is that the radar works, that it shows them where the enemy is, and that's enough. The technology has become invisible through its own success, taken for granted, its revolutionary nature forgotten in the daily grind of operational use. December 17, 1943. A Luftwaffe technical intelligence report lands on Reichsmarschall Hermann Göring's desk, summarizing what German scientists have learned from the captured magnetron. The report is 13 pages of dense technical analysis, but the conclusion is brutally simple. Britain and America have achieved a decisive technological advantage in radar systems. This advantage is now being mass-produced and deployed across all services, and Germany cannot close the gap in time to affect the war's outcome. Göring reads the report twice, then throws it across the room. He spent the past year assuring Hitler that German science is superior, that British radar is primitive, that the Luftwaffe's struggles are due to pilot quality and tactics, not technology. The magnetron report proves him catastrophically wrong. The British aren't winning through courage or determination. They're winning because they can see in the dark and Germany can't. Technology has decided the battle, and Germany has lost. But Göring's rage doesn't change the facts on the ground. RAF night fighters continue to dominate British airspace. Allied radar-equipped aircraft hunt U-boats to extinction in the Atlantic. American bombers use H-2S radar to find German cities through cloud cover that used to provide protection. The cavity magnetron, that simple copper disc with holes drilled in it, has become one of the most consequential technologies of the entire war, saving countless British civilian lives by ending the Blitz, protecting Atlantic convoys by killing submarines, enabling the strategic bombing campaign that will flatten German war production. And most of the people who benefit from it will never know it exists. They'll never see a magnetron, never read a technical report about microwave generation, never understand the physics that makes it work. They'll just know that somehow Britain survived the darkest days, that the bombers stopped coming, that the war turned. They'll know Britain won. They won't know exactly how.